Hey guys, and welcome to another video on my series of videos that I'm doing on electromagnetism. In this video we're going to actually start doing some electromagnetism. The first few videos I just decided to go over some of the necessary maths. If you haven't seen them, I highly recommend that you go back and watch those few videos, as we're going to be using a lot of those mathematical concepts in the upcoming lectures. In this video, we're going to start off by considering electrostatics. So this is probably the simple, kind of the starting point of electromagnetic theory, is that we're going to consider electrostatics. Now, what do I mean by electrostatics? Well, basically electrostatics it means that we're dealing with electric fields, but the key thing is that they are produced by charges which are stationary. So you guys are probably familiar with what a charge is. So a charge is anything which has a charge. It's said to generate an electric field. So say we have like a little point charge here, and let's say it's positively charged, which I'm going to draw in red. That'll probably be the convention. Positive charges I'm going to always draw in red. Negative I'm always going to draw in blue. So we have a positive charge right here, and it's sat in the middle of space. So there's nothing around it. There's just this one positive charge. Now what it's going to do is it's going to generate an electric field. It's going to generate an electric field around this charge. And the electric field is said to point radially outwards from the center. So because it's a positive charge, the electric field lines run radially outward. And a useful thing to always remember is that a positive charge will generate a field which goes outwards. So the way in which I kind of remember it is, if you're more positive, then you're outgoing. So therefore a positive point charge is going to have an outgoing field. So that's the way I remember it. So you're going to have this charge which is going to generate an electric field which goes radially out. So what we're going to do is we're going to just like label the origin right here. And let's say we have a charge. So here's our origin point. Let's say we have a point charge. And when I say point charge, I basically mean that the charge is very, very small. The dimensions of the charge are completely irrelevant. So we're going to have some point positive charge at the center of our coordinate system. So that's all good, but what if we put another charge, some distance, which I'm going to call r, away from the origin? So let's put another charge which doesn't necessarily have to be of the same magnitude. So let's say this charge right here, the charge at the origin, has a magnitude of q1, and this charge a distance r away has a magnitude of q2. Now I'm going to ask myself the question, what is the force that's acting between these two charges? Well, you guys are probably familiar from A level or whatever, that the force is given by Coulomb's law. And Coulomb's law basically states that the force that acts between these two charges right here is proportional to both the product of the two charges, so q1 multiplied by q2, and it's also inversely proportional to the square of the distance between the charges. So not just the distance, but the distance squared. So that is Coulomb's law in worded form, but in equation form, you guys are probably familiar with it as being q1 q2 over 4 pi epsilon naught times r squared. Or you may have just seen it simply written as k q1 q2 over r squared. R squared. And you can pretty easily see that what the k is. The k simply corresponds to 1 over 4 pi epsilon naught, which is actually just a constant, and it's the constant which you have to multiply by to get the force from the charges and the distance, and it has a numerical value of 9 times 10 to the 9 newtons meter squared per Coulomb squared, because of course the units have to balance. Normally I'll just write it like this most of the time, in terms of epsilon 0, which is the permittivity of free space, which you guys probably also know. That has a value of 8.85 times 10 to the minus 12 farads per meter. So this equation right here gives the force between two charges, and it's the mathematical way of expressing Coulomb's law. However, we do know that force is in fact a vector quantity, so I've simply written the magnitude of the force right here, but we do know that force is in fact a vector quantity. And it's useful at this point to define what coordinate system we're going to be working in. So from the three that I introduced in my video on coordinate systems, the one you can see which is probably going to be by far the easiest to work in this particular geometry is a spherical coordinate system. Because remember I said anything which simply has this kind of radial symmetry is much easiest dealt in spherical coordinate systems. So I'm actually going to rewrite the force as 1 over 4 pi epsilon 0. So the charges stay as they are because they're of course just scalar quantities. Charge is a scalar quantity. And the distance is going to be r squared. But how do we represent this as a vector? Well, we simply put a little r hat afterwards, and r hat is the unit vector which points radially outwards. So here's our origin. R hat points always away from the origin, directly away from the origin. So it doesn't actually point in the same direction. The R hat kind of depends on the orientation, or actually to be more precise, it depends on the polar angle theta, because of course R hat at this point points upwards, but R hat at this point points downwards, and obviously it's going to depend on how far around you are or what the orientation is. So but that's how we represent force as a vector quantity. Now you can also express this as 1 over 4 pi epsilon 0 q1 q2, but instead of r hat I'm actually going to write as r vector divided by the magnitude of r. So you guys probably know that to get the unit vector, you take the vector itself and then you divide it by the magnitude of that vector. So normally this would look something a bit like a vector equals the magnitude of a just times some unit vector in the direction of a, which we normally put as a little a hat. So I've re-expressed this as 1 over 4 pi epsilon naught q1 q2 r hat overall, all divided by r squared. So that's an alternative way of representing it, and often you actually know what r hat is a little bit more often than just r vector. So it might actually be easier when solving problems to deal with it using this equation right here than it will be to do it in this equation right here. So yeah. Now the reason why we quantify it as a vector is because of course the direction in which this force acts in is going to depend on the magnitude of the charges. Now of course you guys are probably familiar with the fact that two like charges will repel one another. So the force that acts between these two charges is going to be away from each other. Now we always represent that as a positive force. A positive force acts to increase the distance between the two charges. So this charge right here will exert a positive force on this one, and likewise for the other one. So the distance will always increase. Alternatively, if you have a positive charge and a negative charge, then you guys probably know that they are going to attract one another, because of course opposite charges attract each other. So this is actually going to decrease the distance between here, which is why why this is a negative force and why there's going to be a minus sign between them. And also note that this is not the case for a gravitational field. A gravitational field actually is always an attractive force, and so the force between two large, massive objects with mass, is always going to be negative. It's always going to be attractive. So yeah, but with electrostatics, you can have one of two cases. You can either have a repulsive force or an attractive force. So now I'm going to introduce the concept of an electric field right now. So what is an electric field? Well, I'm going to define the electric field to be the force per unit charge right here. So that's the general definition of an electric field. You guys probably know that from A level. But of course we have two charges right here in our law. So which one are we going to divide it by? Well, let's take our charge at the origin. Let's take Q1, our charge centered at the origin. Well, obviously until we put another charge in, then there's going to be no force at all. But that doesn't mean to say that there's nothing there. And the way in which we kind of represent that is by this concept of an electric field. And the electric field is, of course, just these lines that come radially outward from one charge. So before we put in this second charge, then we just simply have this one charge that's generating an electric field. And the electric field is simply the force divided by the magnitude of the charge right there. And these lines right here are just simply a way of being able to visualize the electric field. So, of course I said that for a positive charge, the electric field lines point radially outwards. So we can actually see kind of why opposite charges attract. And that if we have our Q2 right here, which is a negative charge, then the negative charge is actually going to have its field lines pointing radially inward. So all the field lines are going to point inwards towards the charge, and this is the case for a negative charge. And so you can kind of see that the field lines from Q1 to Q2 in this kind of setup, when you've got a positive charge and a negative charge, just go straight from one to another, which is why they attract. The field lines just flow smoothly between charge 1 and charge 2. Whereas if charge 2 was instead a positive charge, it would have its field lines going outwards right here. And as you can see, this field line is going to sort of clash with this field line right there. And so what's going to happen? Well, the field lines are going to kind of distort and just try and get away from each other as much as possible. So, and try and diverge. So this is why you get a repulsive force for two like charges, because the field lines are actually trying to point away from each other as much as possible. So this is what a little diagram would look like for two like charges. So to get what the electric field is, all we have to do is divide by the test charge, if you like, the charge that that we're kind of putting into the original electric field. So it's going to be the force over charge. So what are we going to get? Well, we're going to get 1 over 4 pi epsilon naught. Now instead of Q1, Q2 over r squared, it's just simply going to be the first charge over r squared. And of course it's going to be in the r hat direction as well. So the electric field is what just one of the charges will produce, whereas the force is going to be what another charge, Q2, will feel in the presence of the electric field generated by Q1. So there you go. I'll give that a highlight because that is a pretty important equation which we'll be needing a lot. So next I want to come on to the concept of electrostatic potential. Now, what is electrostatic potential? Well, I'm going to give it the symbol of V right here. And electrostatic potential is basically, it's defined as the work done from infinity to move the charge from infinity to a point in space. So if you imagine you have some electric field, you don't know what's generating the electric field, but say you've got some electric field right here. And say you have a charge that is completely free of the electric field. So you have a charge that's located somewhere out here. It's a positive charge. It's completely outside the electric field because it's so far away that it doesn't have anything to do with it whatsoever. What is the work done to bring it here, to bring it in the electric field? Well, we're going to have to put in some work to get it all the way over here. We're going to have to sort of fight against the electric field that's kind of stopping it from doing it. And to do that, we have to put in some work. And the electric potential is basically that work. It's the work done, so delta W, divided by the charge of that object that you're trying to move. So that is our formal definition for the electric potential. Now, you guys probably are already aware that there is a relationship between the force and the potential energy of a system. And the way in which we write that is that the force is in fact the negative of the spatial derivative of the potential with respect to position. Now, a simple example of that is the gravitational field. Of course, the potential energy of a gravity field is just mgx, where x is the distance from wherever you're measuring it from. So that's just the potential energy, is just mgx. So what happens when we differentiate that? Well, if we differentiate that with respect to x, then we just get mg. And of course, if we just shove a minus sign in front, minus du by dx is minus mg, of course, just multiply both sides by -1. And that is, of course, the force that's acting. And of course, the reason why there's a minus sign there is because the force of gravity acts downwards. This is, of course, only true for a constant gravitational field. If it wasn't constant, then you would have you'd have to differentiate with respect to x, and you'll get the familiar Newton's law of gravitation. Now, exactly the same thing applies in the case of electrostatics. And so we find that the force, the electric force, is the derivative of the electric potential energy, but instead of writing with respect to x, it's actually with respect to r. And that is because we are, of course, in a spherical coordinate system. We're not going to be using x, so it's going to be r. Now, more generally, I should actually write that this is minus del u right there. And the reason why that is the case is because you could find that the potential energy may depend on the angular coordinates, theta and phi. So it's not just simply du by dr, but it's actually the gradient of u. And the gradient of u may well depend on theta and phi. Actually, to be honest, it's very rare that it does. You may just be given like some kind of problem in which it does, so I wouldn't worry too much about that. Now, what did I say that the potential was? Well, I said that the potential was actually the energy per unit charge. But what did I say the force was? I said that the force is the electric field multiplied by the charge. So what happens if we just divide both sides by charge? Well, force divided by charge is the electric field. And whoops, I missed out a vector sign on there. Force divided by charge is just the electric field. But what's energy divided by charge? Well, the energy divided by charge is just the potential, V, right there. So if we substitute that in there, then we're just going to get that E is minus del V right there. And whoops, there's no minus sign on there. And this is a very important equation right here. It's relating the electric field to the electric potential. And just like in the case of force and potential energy, the electric field is intrinsically linked with the electric potential. One pretty important thing that I haven't mentioned is that this field right here, this value V, is a scalar quantity. So this is a scalar field. It only simply has a magnitude at all points in space. It doesn't have a direction. But when we take the spatial derivative, del, to get the electric field, then of course the del operator converts it into a vector. And of course the electric field is indeed a vector quantity right there with a magnitude and a direction. So this is a very important relation. You're going to be using that thing quite a lot, I would say, for solving lots of different problems. And so, yeah. So that's the relationship between electric field and potential. But what if we're starting out with the electric field and we want to know the potential? Well, we know that for a point charge, the electric field is 1 over 4 pi epsilon 0 times the charge at the centre, I'll just call it Q, over r squared r hat. Well, if we have to differentiate, which is essentially what this del operator is doing, if we have to differentiate the potential to get the field, then likewise you can probably see that you just simply have to integrate the field in order to get the potential. And that's exactly what we do, except we just need to be a little bit careful with what direction we're integrating over. So of course we can see that E equals minus del V, and in the majority of cases, like I said, for the spherical symmetry arguments, that V only depends on R and therefore E only depends on R. So the only direction which we have to integrate along is just the R direction right here. So E dot dr, and so we take an infinitely small slice of R and then we integrate all the way along through R. So say here's our two positions right here, and say the charge is here, and we want to know what the potential is at this point here, away from this charge right here. We basically just do an integral of the electric field multiplied by a tiny infinitesimal slice of R, and then we integrate them. We integrate it up and just sum them all together. So that is how we get the potential, except there is just a minus sign because of that minus sign right here. But the problem is what is the limits? What are the limits of this integral right here? Because of course we kind of need to have limits if we're going to be able to do an integral. Well, what did I define the potential as? I defined it as the work done from infinity to that point. So obviously it starts out here. And then you do put some work in, and then it ends up here. So you do work against the electric field. So the integral limits are going to be between infinity and this point R right here. Now this is quite a confusing thing notation wise. You're actually going to have to deal with two slightly different types of R. There's the integration variable R, and there's also just the generalized expression R. So if I write it in, you'll probably see what I mean. So V equals the integral minus from infinity to R of E dot dr right there. So I know this looks a little bit weird having the variable as both the limit and being the variable of integration. But as you'll see in a minute when I perform this integral, you'll hopefully see what I mean. So let's evaluate what the potential is for a point charge. Given that we know the electric field from Coulomb's law, what is the potential? Well, let's just simply substitute in what the electric field is. So we have our integral from minus infinity to R. And what is E? Well, I said that E was 1 over 4 pi epsilon 0 multiplied by the charge divided by the distance squared, all in the r hat direction. And that is going to be dot producted with the dr vector right there. Now, of course, what is the dr vector? Well, dr is going to point radially outwards, and dr, so what's the unit vector pointing radially outwards? Well, it's just simply r hat. So we can actually express dr vector as being dr simply multiplied by r hat. So there's now a scalar right there, and so therefore we've converted it from being a vector quantity to a scalar quantity, which hopefully makes a bit more sense. So so now we can simply replace that with dr r hat. And so what's this going to reduce to? Well, we have our same old integral right here between minus infinity and r. 1 over 4 pi epsilon 0, which is of course just all constants. Q, which is also a constant, so I might as well just put it upstairs right here. R r hat dot r hat, well, that's just 1. You know, both have a magnitude of 1, and since they're exactly the same, then you're just going to simply get 1 from r hat dot r hat. So that completely goes. The vector bit's kind of now all completely done, and now we just simply have a scalar integral. So we don't have to worry anything about vectors from this point onwards. So that's kind of maybe the hardest bit, is just kind of figuring out what the vectors are, because they can be a little bit misleading at times. But hopefully, yeah, that's before you do any kind of integration. Just know exactly, just try and convert the integral from a vector integral to a scalar integral. And of course, I'll show you guys many different examples of how you do that. So, and of course, there's an r squared, which I missed out. Silly me. And so pretty much all these terms can come out of the integral, because pretty much all of them are constants. This is all constant. None of this depends on r. The charge certainly doesn't, and neither does the permittivity. So we've got our minus sign there. Very important to not forget that. So we're now integrating 1 over r squared with respect to r, which you guys probably know is just simply minus 1 over r. So when we do that integral, we're going to get the constants all multiplied by minus 1 over r, and this of course is going to be evaluated from infinity, I don't know why I've been writing minus infinity all that time, to r. Now this is kind of the bit that I said was a little bit weird, because of course we have r as being part of the limits and r as being the variable of integration. If I was being proper, I would have written a slightly different thing, like r dash or something, to signify that this is the variable of integration. I will be doing that in future, because there will be some derivations in which there is going to be a significant difference. So I will do that. But yeah, so what happens when we evaluate this? Well, we're going to get q over 4 pi epsilon 0. So let's stick in the limits. The minus signs cancel. We're going to get 1 over r minus 1 over infinity right here. Now, you guys can probably see that 1 over infinity is basically 0 in the limit. It goes towards 0. I know the mathematicians won't be happy with me for saying that, but for all intents and purposes, this term is 0. So that can go, and there we go. We've ended up with an expression for the potential, V of r. So this right here should look pretty familiar. This is the potential, or the electric potential of a point charge, which you guys probably know from A level. And of course you can see that it varies as a function of the radial distance r from the origin. But say if we wanted to work out the potential difference, just as a slightly different example, say we wanted to work out the potential difference, delta V, that will, instead of integrating from minus infinity to r, well, what we do in that case is we actually integrate between two fixed points. So let's say that it's RA and RB. You actually do the integral of the electric field over these two fixed points right there. So this is delta V, which is going to be V evaluated at point A minus V evaluated at point B, because of course there's a minus sign there, which I've taken into account. So yeah, that is how you get the electric potential at two known distances, which you're going to want to do a lot of the time, because often you'll be given the two distances in which you are asked to evaluate it from. But if you want to do it generally, then this is the equation to use. And lastly for this video, I want to just introduce a couple of additional concepts of charge. Now, up till now, we've been thinking about charges that are discrete and point charges like this, so plus Q and minus Q. We've been thinking about discrete point charges. But if you remember in my video on the divergence theorem, I actually talked about this idea of a continuous charge. So rather than there being like discrete point charges, you actually kind of have this region in which there's a charge right here, this kind of volume in which there's a certain amount of charge. And this, if you remember, I quantified with the charge density rho, which is the charge per unit volume right there. So that is the charge density. So how do we calculate the electric field from that? Well, instead of using this quantity Q right here, we have to express this quantity Q in terms of rho. And you guys can probably see that if you have to differentiate with respect to volume, the charge, then you have to integrate the charge density over the volume to get the total charge Q. So Q is just simply the integral of the charge density all over the volume right here. So now, of course, this is kind of the case if the density is not constant. Of course, if the density was constant, then you just get rho times the volume. But very, very generally, that is not the case. So I'm going to rub that out. And this is the way in which you properly do it. So you do it by summing over infinitesimal increases in volume. So that's how you get the charge from the charge density. And so how can we relate that to the electric field and the electric potential? Well, the electric potential is quite simple to do. We simply put in V, of course, now is the electric potential, which I'll probably put V brackets of R right there. The electric potential is simply, well, what's it normally? Normally it's Q over 4 pi epsilon naught R for a simple point charge. But of course now we have a distribution charge. So instead of that, well, we're going to get an integral. So we're going to have to get rid of this charge and get rid of this, because of course this R is actually now going to change across the region. So we're going to get 1 over 4 pi epsilon naught, and we're going to get the charge density, which is of course a function of the distance R, all divided by the distance R right here. Now I need to be a bit more clear with my notation at this point. So I'm now going to use R dash as the variable of integration, and R dash is going to be what I'm going to be integrating over, but the potential is of course just as a function of the radial coordinate R, which is what's happened after we've done the integration. Now the distance is actually going to be, rather than just simply the radial distance R, we actually kind of need the distance between the integration R dash and the normal position variable R. So we kind of need this kind of square distance right here. Now in some textbooks I think they use a script R, which looks something a little bit like this. Personally, I'm just going to write the modulus of the distance between the two vectors, because of course R is in fact a vector, and so is R dash, and so I'm just going to be using the modulus distance all integrated over the volume right there. And of course V is also dashed as well. So anything dashed is basically just saying integrate this, and once you integrate that, then you'll be a lot better. But of course it's much more useful if you define the origin point to be where you start doing the integration, because of course one of the terms, this term, will just become 0, and therefore you're just integrating over the volume. So now the electric field, we just differentiate with respect to R, and of course simply put a minus sign as well in front of there. Now the way in which I'm going to do that, you're probably wondering, how do you differentiate this right here? This looks really, really hard. Well, if I make a change of variable, and if I just simply let this let R vector minus R dash equal, or the modulus of that equal, say, I don't know, say this, I'm going to go back and use this script font right here to represent that. Then to get rho as a function of this script R, then we simply use the chain rule and find that rho of R times that is simply rho of R multiplied by the derivative with respect derivative of one with respect to another. And of course, since this derivative is just simply going to end up being 1, then the one is, then they're basically exactly the same right there, so we don't have to worry about that too much. So we're going to get that the potential as a function of this this kind of modulus distance variable, script r, is 1 over 4 pi epsilon 0 times rho of the script r, which is of course exactly the same, dv, of course primed, over this r right here. If we differentiate this script r, then the derivative of r with respect to 1 over r is simply minus 1 over r squared. But of course, when we take the electric field, then we actually get rid of this minus sign right here, because of course this minus sign is going to cancel with that one, and so we just get 1 over r modulus of r squared, which we can also write as r vector over modulus of r cubed right there, because of course there is going to be an r hat right there. So if we substitute all that in, then we get 1 over 4 pi epsilon 0 times the integral of, and now for the geometric term, we're going to get r, we're going to get script r vector over script r cubed, all multiplied by rho of script r, integrated over the volume right here. So I know it looks a little bit ugly, this formula, and personally I'm really not a big fan of this kind of way of writing it, and you know, normally I quite like to just simply try and consider it using the other representation and using simple things like that. So yeah, so this is going to be the case of a continuous set of charge. And the last thing I want to do is that the exact same thing can be applied, but instead of a volume charge, you have a surface charge, sigma. And sigma is dq by dA. Now, this is exactly the same thing applies, but instead of volume, every time we see a volume term, we replace it with an area term, or I've actually been using ds right here for sort of surface. That's what I'm going to be using from now on instead of A. So that's the surface charge density, sigma. It's the charge per unit area. It has units of coulombs per square meter, whereas this of course has units of coulombs per cubic meter. And again, we get the exact same thing. You get the field and the potential in the exact same way. So yeah, that is an introduction to electrostatics. In the next video, we're going to be looking at Gauss's law. And Gauss's law is incredibly useful, incredibly important, so don't miss out.